Now I am going to move on to a different set of problems. So up until now, we were talking about given a set of formula, what can I prove? Can I prove a particular formula? This was the inference procedure we were working on, and again that's beautiful. We have got two strategies. There are many other strategies. But now we will talk about model finding. Model finding means find the assignment to variables that make the formula true. So I give you a SAT formula like A and B, and I want you to find a model for it. Any one assignment of variables that makes the formula true. If my formula is A and B, which model can make this formula true? A equal to 1, B equal to 1. If my formula is A or B, how many possible models do I have? 3. And I can give any one of them. That is the model finding problem. Now, why do we want to study it? It is also called the satisfiability problem. Given a formula, find as an assignment of variables that makes this formula satisfiable. It is the canonical NP complete problem. Now, we have discussed this before, right? What is NP? NP stands for? Yes, what's your name? Yes, Abhishek. Non-deterministic polynomial time algorithm. It's a polynomial time algorithm, but in this non-deterministic world. Now, it will take you some time to appreciate what does NP really mean. But here is your homework, serious homework. Go home and read about NP completeness. Even if you don't understand it, read about it. The next time somebody asks you what is NP, you should not say not polynomial, because that is not true. In fact, if you know that it stands for not polynomial, you will be the most famous person in computer science today. Because the biggest question in computer science today is P versus NP. Because P means polynomial time, and if NP means not polynomial time, then we are done basically as a computer scientist. The AI folks are still useful. But that is the question for theory of computer science, entire theory of computer science. That is the, I wouldn't say $1 million question, no. It has to be at least a $1 billion question, if not more. Okay. But what we know so far is these NP complete algorithms, you can verify their solution in polynomial time. But so far you cannot compute their solution in polynomial time. But you can compute their solution in polynomial time if you were given this computer which could take the right decision at every step non-deterministically. And such a computer is called, abstraction of that is called a non-deterministic Turing machine. Now that goes into a certain level of theoretical depth which you will study in a theory of computation or a complexity course. We will not talk about this. But we will say that we love solving NP complete problems, and for that you need to have some idea about what are non-NP complete problems. They are those problems which you have not been able to find a polynomial time solution so far. So therefore, only solutions that exist for them are exponential time right now. And this is talking about NP, but what is NP complete? NP complete says that if you solve this problem, any NP complete problem, that any other problem in NP can be converted into this problem, and then you can use the solution of this problem to solve that problem. And we will show you examples. Because it's such a canonical problem, because everything can be converted to this problem, therefore, if you have a good solution for a SAT algorithm, SAT is the short form for satisfiability, then you have a good solution for a lot of problems in the world. And therefore, it has a ton of applications. And now what is beautiful from an AI point of view, this is all theory so far, but what is beautiful from an AI point of view is the state of the art solvers, the current solvers for satisfiability problems are amazingly fast, like blazingly fast. And how did they get there? We will talk about some insights. But let us first see why SAT is so important. So let us take some examples and try to convert those problems into a CNF formula or a logical formula such that if I can give a satisfying assignment to that formula, I have solved my original problem. And here is one such example. I give you two circuits, two complicated circuits. These are not complicated, but let's say I give you two complicated circuits. In this case, the first circuit is A and B are ANDed to give C. In the second case, A and B are NOTed and then NORed to give C prime. And now I ask the question, do circuits compute the same function? This is very important in circuit optimization. Suppose I have a formula that somebody gave me. Let's say I want to optimize it with minimum number of gates and so on and so forth. And then after I have done all this, I want to make sure that I didn't make a mistake. The original circuit and this circuit are actually equivalent. How do I do it? I do it with what is called, in this case, I do it with satisfiability problem. So now I will turn it around. So when I want to ask the question, are they equivalent, I will instead ask the question, is there some assignment which gives different values to C and C prime? Now why do I ask this question? Why can't I ask, are they equivalent? Somebody has an answer. Who has an answer? Okay. Yes, you are Ansh, yes, sorry. In that case, I will have to check all the possible assignments. And what can satisfiability give me? Any one possible assignment. See, satisfiability is it's limited. You give it a problem, it will give me one possible assignment. You can always use theorem proving to prove that C is equivalent to C prime if it's a Horn clause, or if you can use resolution. You can also use resolution here. Nothing wrong with it. But satisfiability, if you want to use satisfiability, you will have to use a problem formulation in which one assignment does the job. So let's do this. So the first step we will do is we will encode the current logical formulas. So you will say C is equivalent to A and B, C prime is equivalent to not D or E, D is equivalent to not A, E is equivalent to not B. I have defined intermediate variables D and E for this point. This is good so far. Now the next question we want to ask for a satisfiability problem to check circuit equivalence is, what else do I add to my formula? Should I add C equivalent to C prime? If I add C equivalent to C prime and ask for a satisfying assignment, what will happen? It will give me one satisfying assignment. It is possible that there is one satisfying assignment, but it is also possible that there is some assignment which makes C and C false. I mean C not equal to C prime, and we will not know about it. So we have to somehow reverse it. So we will add not of C equal to C prime or C not equal to C prime, which and you will use all those tricks to convert it into a clause. Now if I have a satisfying assignment, what have I done? I have got an assignment where they are not equivalent, and that means that they are not equivalent. However, if I don't get any assignment, then I know that they are equivalent. Let's take another example. We will do several of these so that you can learn the importance of satisfiability problem. Okay, so I'll let you think. So we need to create a SAT formula such that its satisfying assignments gives me, solves the n queens problem. Let's say solves the 8 queens problem in this case. Now whenever I have such a problem, the first thing I need to do is to figure out what will be the guess? Logical form representation CNF. No, we will always have a CNF form eventually, but a CNF form is over a set of variables. So the first thing we need to know, we have to model the world. See, this is a real world n queens problem. There are real chessboard, there is real queens, whatever. But now we are creating an abstraction in the logical representation. We are giving it this information to the agent in logic So the first thing we need to know is define symbols. What is each variable? What does it mean? Now remember, in logic, a variable is always binary. It's only true or false. So what true-false variables can we define which might help us in solving the n-coins problem? So this is going to be interesting, right? One assignment of those variables should tell me exactly where each queen is placed. And it's a 0-1 assignment. Can somebody think of such variables? Not clauses, just variables.
Queen is present or not. Whether the queen is present or not.
Where? Queen is present or not? Present as in it's present in the class? In the chessboard? At a specific position. Alright. So you say that I will define xi or qij such that qij is true if the queen is present in ith row jth column or ith column jth row. I don't know exactly how this thing is written, so we'll figure this out. Let me see how this thing is written. Ith column and jth row. Okay, I think this is how it is written. So we define this. Let's say we define this. So how many variables did we define for 8 queens problem? 64 variables. So far so good. Now I need to somehow encode the constraints of my problem such that one satisfying assignment gives me the solution for the n queens problem. Alright. So now tell me what should these constraints be and how do we represent them in logic. People who haven't spoken, let's get towards this is not too hard. If you think about it, you can get it. So let's see somebody who hasn't spoken so far. Somebody who's feeling brave enough to suggest an answer. You want to say something? Not yet? This is not very hard. What is the major problem with n queens? What do we want to make sure? No two queens are attacking each other. So how do we say this? Now we may not be able to say it in general, but we can say it for pairs of positions. So now that is your hint. So now somebody raise your hand. Yes, what's your name? Ashray. Yes, Ashray.
So we can have like a difference between I1 and I2 and J1 and J2 should not be equal.
Okay, so difference between I1 and I2 and J1 and J2 should not be equal. So you are trying to model it in general for a diagonal, right? That is what you are trying to do. Very good. But remember that our language is ands, ors, implications. So whatever we say, we have to say it in that language. We are not given the minus operator. And we can't even go to the index of the variable. The variables, we have 64 variables now. It's much simpler than what you did. You did something very complicated in your brain. You have to do something much simpler. Let's take 2 positions. Let me take some positions. Let's say 1, 2 and 2, 1. Very simple. Forget general diagonal. We want to say that, what do we want to say about Q1, 2 and Q2, 1? Both can't be 1. Very good. That's it. That is the only thing we have to say. We have to say both Q12 and Q21 cannot be 1 at the same time. What logical formula gives me that? Not of? Let's do this together so that this is actually really, really important. So what formula tells me that? So we defined Qij equal to 1 if queen is in ith column, jth row. Now we are talking about attacks, and let's say we talk about Q12 versus Q21. So we want to say that both can't be 1. And how do we say it logically? Not of perfect, not of and of Q12 and Q21. Basically it says if you can't have Q12 and Q21 at the same time, which is equivalent to saying not of Q12 or not of Q21. And then let's think about what this means. It basically says either Q12 is false or Q21 is false, which is equivalent to saying both can't be true. Now let us suppose I wrote this formula for all such pairs of attacking positions. For all pairs of attacking positions, I wrote this. Is it sufficient? Is this enough? This is the most fundamental thing. This makes SAT a little complicated, but this is very important. Suppose I gave this problem to my SAT solver and gave me a solution. Will it always be the correct solution? What have I not captured here, or what solution could it give which will be meaningless? No queen on the board. Excellent. I'm so happy you got this. My SAT formula could say, don't put anything. You are saying don't put Q12 or don't put Q21. Let me not put anything. I have not said that please put queens. How do I say please put queens? All of all the rows should be 1, or all of all the columns should be 1. So for example, I want to say that there should be at least 1 queen in the column. So how can I say it? First column, either Q11 should be true, or Q12 should be true, or Q13 should be true, or Q18 should be true. Okay? And now if we are able to solve this problem, that means it would satisfy all these clauses also. So that means it would get a queen in every column, and it would make sure that no 2 pairs of queens are attacking because of the previous formula, and so overall we would be able to solve the problem at hand. One more example. This is fun stuff, by the way. It is possible that in some exam we give you a new problem and say, give me a SAT encoding for this. This is really saying, I have a physical problem, I want to model it computationally, this is my model. It may be a good model, not good model, but it's a model. And because these are formal problems, this is an accurate model. In the real world, it's an approximation. In a formal world, there is no approximation. Let's do our favorite map of Australia problem. And this is also very interesting because, okay, so here is a simple thing. Is a SAT problem a CSP problem? See, what is in a CSP? You have a set of variables, a set of domains, and a set of constraints. What is a SAT? You have a set of variables, the domains are true, false, and you have a set of clauses which are like constraints. So eventually every SAT problem is a CSP problem. But is every CSP problem a SAT problem? Well, every discrete CSP, every discrete finite CSP can be converted into a SAT formula. And here is how. This is called proof by example. So don't use that in your exams. If I ask you to prove something and then you say, let us say for example, and then that's it. That's not a proof, right? But in classes, I am allowed. Okay, so I am giving you the map of Australia. My goal is to create a SAT formula such that the solution of the SAT problem is the solution of the CSP problem. What will be my variables? Now you have a hint already from the previous slide. What should be my variables? I have 3 colors, 7 states. How many variables do I have? 21 variables. I have a variable, a new SAT variable for every variable value pair. In this case, my variables are Western Australia is red, or Western Australia is green, or Western Australia is blue, and Northern Territory is red, Northern Territory is green, and so on and so forth. Now, I need to say some things. some basic things about CSP, and then I have to model constraints. Let's talk about the basic things in the CSP. What are the basic things I need to say? Somebody, raise your hand. Not constraints, just basic, so that I don't get into all falls and things like that. What are the obvious things I need to say so that it's a well-formed SAT problem?
Every state needs to have at least one.
Every state needs to have at least one color. So give me one example. Let's say for Western Australia, what will be the clause? XWAR or XWA green or XWA blue. There is one other obvious constraint that I need to add. So it needs to have one color, and at the back, yes, what's your name? Kiran, yes, Kiran. It should at most have one color. Because up until now, we have only said it should have one. But we haven't said it can't have more than one. It could decide to have all colors in Western Australia, then things will become crazy, right? Because it's a SAT formula. You have to think like SAT. You are saying that we are giving no initial constraints. So now you have to add all those constraints. But these are general constraints. You learn to add these general constraints. So how do we add that a variable should not have two colors? Sorry? Pairwise ANDs and the negation of that. Or alternatively, the same idea that we had last time, that Q12 and Q21 both can't be true. In the same way, we will say WAR and WAG both can't be true. WAR and WAB both can't be true. WAG and WAB both can't be true. And now, finally, last but not the least, we should add the neighborhood constraints. And give me any one neighborhood constraint, somebody.
So ex-Western Australia red and ex-Northern Territory red, we take the
Not of ex-Western Australia red and ex-Northern Territory red. Very good. So this is what you have to start getting used to. The reason I am spending time on this is because this is an important skill. There will possibly come a time in your later life when you are given a very complicated, constrained problem without uncertainty. Now these are all deterministic problems actually. These are formal problems. There is no notion of uncertainty, probability and so on and so forth. Now this would not come up in robotics. But let's say you wrote a software and you want to check whether the software is accurate or not. It's a mission critical software. It is going onto a plane on NASA or a rover on NASA, or it's going to be used by Boeing. What will you do? You will use SAT solvers, believe it or not. And you will have to convert your problem, the formal problem, model checking problem, into a SAT problem and then give it to a SAT solver. This is exactly what you will have to do. That's why I am pushing on you to learn this skill. So the suggestion that was given, sorry, what is your name? Abhyuday, by Abhyuday, is that not Western Australia red or not Northern Territory red. And you do it for all pairs of states and all colors. And this allows us to formally model the graph coloring problem in SAT. There are many other applications. For example, diagnosing a malfunctioning device is called model-based diagnosis. If the design of the device is known and already expressed in the form of a logical representation. And what we do is we can observe, unfortunately only observe states of certain parts of the device. A lot of them are hidden. And that leads to this idea of model-based diagnosis, where we create a logical formula in which how the device works, and then we have some components that can break, and each formula says whether this particular component is okay or not, and the diagnosis is the smallest set of not okay assumptions that are consistent with what is actually observed. I can skip some of the details, but at the highest level, you make some observations. You initialize a set to assert that all components are working properly. You first check that that is not possible. Once you check that that is not possible, you have been able to reduce false. Then you delete propositions from your assertion one at a time to check if this was deleted, will that now be consistent? If it will be consistent, then that's a diagnosis. And then you go into the car and you actually check that component somehow, and then you try to fix it, right? So for example, if I have propositions like engine is running, gas is in tank, clock is running. Now this you can observe. But then there are some internal propositions, like whether fuel line is working okay, whether battery is working okay, whether cables are okay, whether clock is okay. Now I don't know about these. And then there are some things you might not even be able to, check, and that they are somewhere in the middle. They are not even the diagnosis, there's something in the middle, like gas is in the engine or not, power is coming to the plugs or not. And then you have a model for the device, that if gas is in tank and fuel line is okay, then gas is in the engine. And if gas is in the engine and plugs are getting power, then engine is running. And if battery is okay and cables are okay, then power is coming to plugs. And if battery is okay and clock is okay, then clock is running, right? So now this is your model for the problem. And you suddenly observe that engine is not running, but there is gas in the tank and clock is running. And now you have to hypothesize what must have happened in the car to figure out where to look, where to try to fix the problem. So the first thing you say is F union observations, union assumptions consistent? Of course, that is not consistent, because if every assumption was true, the assumptions here were fuel line is okay, battery is okay, cables are okay, clock is okay, then engine should have been running, engine is not running. So now you say, all right, let me think that maybe fuel line is not okay. So let me remove fuel line from my assumptions and then check that is it a diagnosis, and if I can have a satisfying assignment there, then it's a diagnosis. Similarly, I see, okay, is battery the problem, and does it give me to false? And if that gives me false, then it is also it's not a diagnosis, right? So in the first case, this becomes true because fuel line okay can be a possible reason for why engine is not running, so it is a diagnosis. In the other case, battery okay does not lead me to battery not okay does not lead me to engine is not running, so that is not a diagnosis, right? And so typically, if F is a Horn clause, then consistency test takes linear time, and if you only remove one, so that, remember it was linear time, Horn clause inference is linear time. So if you only remove one diagnosis, then the total time taken is order n square. So you are saying only one thing went wrong at a time. I don't know if you realize, if you see House MD, you will see, have you seen House MD? Some people have seen House MD. You should see House MD. It's an absolutely fantastic serial. It talks about rare medical conditions and how they diagnose it by making mistakes. So he always believes that there is one problem that is causing everything. You can't say that, you know, there is a problem in his nerve, and there is also a problem in his lung, and also there is a problem in his, you know, brain. That doesn't work. There is one underlying diagnosis which is really the problem due to which the particular symptoms are coming out. So in the same way, if you are looking for only one fault, then it will take order n square time, because you'll have to try n of those problems, and every inference will take order n time. Then double fault would be n square, triple fault would be n cube. I think we have discussed that earlier in Deep Space One, this spacecraft, NASA used a SAT solver. They compiled the whole system schematic into a 7,000 variable SAT problem and use a SAT solver to do diagnosis, right? And of course, we have discussed this earlier, but they were not able to test the diagnosis system in the real world because nothing went wrong. And so they simulated faults. And when they simulated faults, the diagnosis system was able to diagnose it, and the system was able to repair it, right? And these are the three faults that they simulated. They failed an electronics unit, the system reactivated it. It was called remote agent. They failed a sensor. It was starting to provide false information. Remote agent recognized it and stopped using that particular sensor. And then some thruster was stuck in an off position. It was not turning on. So the remote agent detected it and compensated for it by switching into a mode that did not rely on that thruster. SAT solvers have had an amazing impact on our community and in the real world. And in the next class, we will talk about how to solve satisfiability problems. In this class, we learnt about how to model a problem as satisfiability.